Hello students, I welcome you all on my YouTube channel. In last video, we looked at definition of exact differential equation, and also we solved some problems on exact differential equation. Now in this video, we will be discussing equations which are not exact, and we are going to find out their solution, right? We will see how to solve the equations which are not exact, right? So without wasting any time, let's start. So I'm gonna give you an example of the equation which is not an exact equation, right? So see here, y dx minus x dy is equal to 0. Now here m is equal to y and n is equal to minus x. If you try to check this equation is exact or not, we will have to find out curly m by curly x, which would be equal to curly x over curly m by curly y, right? It is equal to 1, and curly n by curly x is equal to minus 1. So therefore curly m by curly y is not equal to curly n by curly x, right? Therefore we can say, therefore given differential equation is not exact. This equation is not exact. Now if you want to solve it out, we don't know how to solve it. Until now we don't know how to solve it, right? So in order to solve this, we will be converting this equation into exact differential equation. How to convert this equation into exact differential equation? So the idea of integrating factor come into picture. See, if I multiply this equation on both the side by 1 upon x square, see what happens. Multiplying 1 by 1 by x square. See, it becomes 1 over x square y dx minus x dy equal to 0 time 1 over x square, which is 0 again. Now instead of 1 over x square, I would be multiplying it by 1 over y square, so that this problem would be simple. Okay, so that it would be simple for me to tell you that this is the integrating factor of this equation. Otherwise it is possible with 1 over x square also. So now y dx minus x dy upon y square is equal to 0, right? Now you see, we saw in earlier videos that d of x over y is equal to, using quotient rule, y square y as it is differentiation of x minus x as it is differentiation of y. So and therefore this equation is exact now, because we are able to find some u x over y such that such that exact differential is equal to this equation, right? Or we can also check using m and n here. So simplifying this equation, it becomes y dx over y square minus x over y square dy is equal to 0. So 1 over y dx minus x over y square dy equal to 0. Here now m is equal to 1 over y and n is equal to minus x over y square. Okay, so curly m by curly y is equal to differentiation of this, it is 1 over minus y square, and curly m by curly n by curly x would be, y would be constant here, so 1 over minus 1 over y square. So see, we have made this equation exact. We have made this equation exact by multiplying with this equation and a factor 1 over y square. That's why this equation became exact. Okay, so this factor or this function which is multiplied with this equation, after which this equation became exact, is known as integrating factor. Integrating factor. Okay, integrating factor. So let us define this function now. Integrate, what is integrating factor? Let me write it here. Integrating factor. An integrating factor, or you can write a function mu of x and y is said to be is said to be integrating factor of a given differential equation if the equation if the non-exact equation becomes exact after multiplication multiplication with this function, after multiplication with this function mu x y. Example here we discussed earlier. Example is this equation is not exact, and we found out that 1 by y square is integrating factor of this equation in this case. Okay, because earlier it was not exact, and after multiplication with this factor, multiplication made it exact. So that's why we will call it integrating factor. Okay, so now we are going to see some more integrating factors. Okay, so we are going to make a table of integrating factors. Let us see how many integrating factors are there of y dx minus x dy equal to 0. We saw 1 by y square is integrating factor of this equation, and then equation became exact and it was equal to y over x over y. Also, as I told you earlier, 1 by x square could be also integrating factor of this equation. See how? If I multiply this equation, we know this equation is not exact. So if I multiply this equation by this integrating factor, it becomes y dx minus x dy over x square equal to 0. Now if I take minus sign out, it becomes x dy minus y dx over x square. So I can write it as, now it has become I can write it as exact differential of y over x, because using the quotient rule, x square in the denominator and x as it is. Okay, dy minus y as it is, differentiation of second function. So this is first function, y is first function, this is second function, right? So therefore it is equal to, it could be also written equal to d of minus y over x, right? So therefore we can write it as d of minus y over x. Okay, also if I multiply this equation, okay, I'm going to multiply y dx minus x dy with 1 over x into y. See, it becomes equal to dx over x, okay, y minus x dy over xy. Cancelling this, you get dx over x minus dy over y. So it is equal to, integration yields, this is equal to, this can be written d of differential of log x minus differential of log y, because it is equal to this. When you integrate when you differentiate log x, it gives 1 over x dx, right? Dx over x, and log y gives dy over y. So therefore these two are equal, and thus we are able to write it in this way. Or also we can also write this log of x over y using log formulas, right? So equation has become exact, therefore 1 by x into y is also integrating factor of this equation, and exact equation becomes d of differential of log y over I'm sorry, x over y. We are going to find out another integrating factor of this differential equation. So see, y dx minus x dy is equal to 0 if it is multiplied by x square plus y square. It becomes y dx minus x dy equal to 0. Now you can write it as you can write it as exact differential of tangent inverse y over x, because here you see what is differential of tangent inverse minus tangent inverse y over x. It is equal to what? We know tangent inverse, differentiation of tangent inverse is equal to differentiation of tangent inverse x is equal to 1 over 1 plus x square. So here also it would be equal to 1 plus y over x whole square, and in numerator differentiation of y over x. Now again solve this. It is equal to, using quotient rule, x square as it is in the denominator x square, and here x as it is dy minus y as it is differentiation of x, upon taking LCM it is x square plus y square. After squaring, this will get cancelled, and thus you will be left with xy x dy minus y dx over x square plus y square. Okay, so there is minus sign outside of this equation, so if you apply minus sign here, so this becomes same as this equation, right? It is equal to this in negative, this in positive now. So thus we can write this thing is equal to d of minus tangent inverse y over x equal to 0. Thus we are able to make it exact. Hence we can say 1 by x square plus y square is also integrating factor of given differential equation, right? So let me write it here in a chain. One by x square plus y square also is also integrating factor of this equation, and after multiplying it equation becomes exact, and which is equal to d of minus tangent inverse y over x. Okay, now we are changing this equation. This is no this is exact equation actually, but still it could be have integrating factor, right? X dy plus y dx. We know this is an exact differential equation, but still we can find out uh, some functions, okay, of x and y, such that in such a way it when which when multiplied to this equation it still remain exact differential equation. It doesn't become non-exact, right? So here you see, if we multiply it by 1 over xy, it still remains exact differential equation, and it becomes equal to differential of log xy. Okay, and also you see, if this is another equation, x dx y dy, it remains exact if it is multiplied by x square plus y square, and it becomes equal to differential of half log x square plus y square. Okay, so this is all about integrating factor. Now we will prove a result. Result is a theorem on integrating factor. Prove that it is all about numbers of integrating factor. How many integrating factor are possible for a exact differential or non-exact differential for a differential equation? Okay, how many integrating factor we can find out for a differential equation? So this is all about this thing, right? Number of possible integrating factor which are infinite. Okay, which is infinite. Prove that the number of integrating factor of differential equation mdx plus ndy equal to 0 is infinite. Proof: the given differential equation is mdx plus ndy equal to 0. Now let mu be an integrating factor of this equation of given equation, right? We are just assuming the possibility of one integrating factor. Now we will be bringing out more and more integrating factor from this u now. Okay, so therefore mu, okay, before this multiply this equation by mu. Okay, multiplying both the sides of 1 by mu, we get what we get: mu mdx mu ndy equal to 0. So see, if this equation was exact, then this remains exact. If this equation was not exact, then also it becomes exact, right? So we can write which is exact, right? By the definition of exact differential equation, now there exists some u such that therefore mu mdx plus mu ndy is equal to du, because it is exact, right? Since it is exact, there exists a u such that mdx plus mu ndy is equal to du. Now if we multiply throughout by fu, see what happens. Multiplying throughout by fu, okay, we get what we get: mu fu mdx plus mu fu ndy is equal to fu du, right? So see, it could be written this is equal to this thing, it could be written equal to d of fu, right? So therefore it is still exact, because it is, we are able to find some u which is equal to fu such that this equation is equal to differential of this. Therefore this equation is still exact. Thus we can say this is also an integrating factor of the given differential equation. Okay, therefore mu fu is also an integrating factor of 1. Since there could be infinite function of, since there could be infinite functions of u, because this is function of u, right? This is function of u, and function of u could be infinite, like it could be u square, it could be it could be u cube, it could be u4, it could be u5. Okay, so therefore there exist infinite uh, functions of u, hence we can say the number of and therefore the number of integrating factor is also infinite. Therefore number of integrating factor is also infinite. Okay, so done with the theorem. Okay, so let us do some problems on integrating factor. This is it for today. In next video we will solve some problems on integrating factor. Okay, see you guys.